So now we're going to be moving on to our other section where we're going to be dealing with problems that are not really related to the other sections, and they're kind of like in a section of their own, right? So these questions are going to be relating to like bit manipulation or like, I don't know, like random stuff like dealing with parentheses and just stuff in that nature, right? So our first problem is going to be number of 1 bits, right? So given an unsigned integer, we are supposed to be returning the number of 1 bits it has. So in example 1, we have n is equal to this large 32-bit number, right? So this is 32 bits. And we're supposed to return how many ones there are. So this is 1, 2, 3. So there's 3 ones inside of this 32-bit integer, and so we return 3, right? Similarly here, for this 32-bit binary representation, we have only one 1, right? And that's why we return 1, as there's only one 1-bit, right? For this question, we have all of these. So this is supposed to be 32 bits, and only one of them is a 0, and the rest are 1. So we're going to be returning 31, as there are 31 ones, right? So that's kind of the idea of the problem. So how would we actually do this? So before we think about 32 bits, I think it's probably beneficial to first look at like a smaller problem, which would be like 4 bits. So for example, if we had 0, 1, 1, 0, how are we going to return how many ones there are in this number? So I think a really helpful thing that we can do is have a integer, and we'll call this integer like a. We'll have integer a, okay? So this represents n. N is the input that we have, right? N here is the input that we have. And let's say they give it as this 4-bit for now, okay? 4-bit integer for now. And we're going to have an a, and it's going to be equal to 1. Okay, how do we represent 1 in binary? We do 0, 0, 0, 1, right? So only the last bit is actually on, and this will represent 1. So what we're going to do is we are going to AND these two numbers. So we're going to perform the AND operation on these two numbers. So we'll just, let me just copy this, and I'll paste it down here, okay? What we're going to do is the AND operation. Let's just write it like this. So these two numbers, when we AND them, what do we get? Well, if you're unfamiliar with this operation, basically we're going to look at each bit, and if both of them are on, if both of the bits are 1, then the output bit will be 1 as well. Otherwise, it's just going to be 0. So both of the bits have to be 1 in order for the resulting bit to be 1. So in this case, this is a 1 and this is a 0, so the output is 0 because not both bits are 1, right? They both have to be 1. Same thing with this one, we're going to be 0. Same thing with this one, it's going to be 0. Same thing with this one, it's going to be 0, okay? What did we just find out? Well, the reason we set our a equal to 1 in the beginning, the reason why we use this 1 is to check if this bit is actually on, okay? If this bit is a 1, that's what we're checking. So when we get an output of 0, we know that this bit is not actually a 1, because if it was a 1, then these two would produce a 1, right? This one would turn into a 1, and then we'd know that this bit is a 1, and then we'd increment some sort of counter, right? And then after we do that, let's say we have a counter, right? Let's set our little counter up here, and our counter is equal to 0. So now what we want to do is change our value of a. So now our a, we're going to shift this 1 to the left, right? So let's remove this, and this, and this. We want this a to now be this. And why do we do this? So that now we can compare these bits, okay? Compare this bit and see if it's on for our input. So at this point, we're going to AND these two numbers, and we're going to get 0, as these two are 0. We're going to get 0 for here, and then these two are on, right? These two bits are 1s, So this is going to be 1, and then this is going to be 0. And anytime we get a result here that's not a 0, then we know that this bit right here is turned on. So at this point, we're going to increment our counter right here to 1, as now we found our first 1 bit. Okay? Oops. So that's good. So now let's erase this and then shift this to the left. Now we're going to be dealing with 1 or 0, 1, 0, 0 now, okay? And that's to compare if this bit is actually a 1, okay? So we're going to do the AND operation for this. And now, what do we get? We get 0, 1, as these two bits are on, 0, 0. And right here, we notice that this is not a 0, right? And anytime this is not a 0, we know that the bits that we just compared were on, right? So at this point, we're going to also increment our counter once again, as we found another bit that is a 1 inside of our input. And we'll do this again one last time and shift this to the left. So now we're going to be dealing with 1, 0, 0, 0. So this is our A this whole time, right? We're shifting the 1 in our A, okay? Our A started as 0, 0, 0, 1 up here, and oh, sorry, I just realized you were not able to see this counter, but I was incrementing it. But our A started at 0, 0, 0, 1, and our A has always been this number, right? And each time we do this operation, we shift the 1 that started here, we shift it to the left, right? That's what's going on. And now our 1 has shifted all the way to this point, right? So we're reaching the last iteration of our loop that we're going to have, and then we're going to do this AND operation one more time to see if this bit is on for our input value, right? We're going to see if this bit is on. What do we get when we AND these two numbers? We're going to get 0, oops, 0, 0, 0, 0, as none of these bits are matching ones. So since this is 0, then we know that we don't need to increment our counter. And at this point, our 1 has been shifted all the way to the left, which means that we can actually break out of our loop and return our counter, which is 2 right here. And the 2 represents that there are 2 1s inside of this input, right? There's 2 1s right here, 1 and 2. That's what this counter represents. And that's our algorithm. So let's go ahead and implement this. So we had our integer a, which started at 1, right? 1 right here, this is the same thing as writing 0, 0, 0, 1, like this, right? And now we could start our loop, but instead of, so here this would be a loop of 4, right? Because we started at 0, 0, 0, 1, and then we did 0, 0, 1, 0, and then we did 0, 1, 0, 0, and then we did 1, 0, 0, 0. So that would be a loop of 4 for each bit that we have to compare. But this will be a 32-bit integer. So we're going to be doing a loop of 32, right? So int I equals 0, I is less than 32, I plus plus. And each time we're going to be checking if our n and our a, if it doesn't equal 0, right? As I said, anytime that our when we AND the two numbers and it didn't equal 0, we're going to increment our counter. So I'll just have an int counter up here that starts at 0. And then here, I'm going to increment the counter, because that means that we found a bit from our input that is actually on, right? And yeah, that's literally it. At the end, we're just going to return counter, and we could run this to make sure that it's right. Oh, all right. We want to put a parentheses around these to indicate that this has to be done first before we do any comparisons over here. Oh, if oh right, I forgot to include the shifting, right? So you remember when our A in the beginning was 0, 0, 0, 1, and this AND operation produced a result of 0, 0, 0, 0. So that's cool. But now I didn't incorporate the whole shifting left, right? So how do we actually do that? Well, there's two ways that we can do this. The cool way would be a left left equals 1. So what this means is we're going to shift everything to the left by 1 bit. Okay? So what that's going to do is shift this 1 here, shift the 0 here, shift the 0 here, okay? And it's going to fill the last bit with a 0. That's what that's going to do. Or we know that this is binary. We could also do a times equals 2, okay? Because each time we actually shift to the left, we're just multiplying by 2. And that's a cool little thing to know about binary. So we could do either or. Let's just do the cool way, which is this way. We will run this and make sure that it prints out the right result. So it does. We'll submit that. Okay, cool. So what's the time complexity of this algorithm? Well, we are iterating 32 times, right? This will always be 32 iterations. So we could just call this O of 32. This could be considered constant space, right? Because it's always going to be O of 32, because we're always just checking a 32-bit integer. And our space complexity is simply O of 1, as we're only allocating space for this integer A, and our int counter, which stores how many ones are actually stored inside of our input, right? And if you want to simplify this to O of 1, you can, but I'm just going to write O of 32 to make that clear. But yeah, that's the solution to number of 1 bits inside of a binary string.
If you like this video, make sure to check out my course on Udemy where I go over how to approach and solve LeetCode's top interview questions in Java. This will help you get more comfortable applying concepts like arrays, strings, linked lists, binary trees, dynamic programming, object design, and many other concepts in order to solve problems effectively and ace your interviews. So if you're interested in it, feel free to check it out through the link in the description. And with that being said, I hope you guys have a good rest of your day, and I'll see you in the next video.